So, hello everyone. My name is Vinay Bhardwaj, and I'm going to present my IBM Advanced Data Science Capstone project. And I have prepared this project on IPL cricket data analysis. And for those of you who understand cricket a little bit, it will be very easy to understand. But I'll be explaining all the aspects of cricket side by side as I do this presentation. So IPL is the world's largest cricket tournament played in the world, around the world, and it's organized by India generally. IPL stands for Indian Premier League. So I'll explain the use case. What we are going to do over here is we are going to fetch the data from Kaggle, and we are going to create new data sets that are not exactly present in the dataset, and we'll create new features from high level data to represent real time match situation which is not actually present in the dataset. So there's a certain data available, but we don't have actually the data that our model will be happy to accept and do predictions on. And finally, what we will do is we are going to create a model that will predict the total score for a match in an innings. So there are two innings in a match. You can't predict the score for the second innings because second innings happens when the first inning score is done, and the second innings team generally chases that score. So we are going to predict the first inning score, and you will be able to understand the data once I clarify the data set. So my data has been fetched from Kaggle. It's fetched from here IPL Data, and it has two data sets. One is the matches data set, and another is the balls data set. So there have been 11 seasons till now for IPL from 2008 to 2019. The 2020 version was just cancelled because of COVID-19. And our dataset has two CSV files. One is matches, one is deliveries. So every match has roughly 120 deliveries. That is not counting the penalty deliveries. That is a bowler bowls a wide or a no ball or something like that. So the deliveries can be they can be extra deliveries in the match, but generally there is 120 deliveries per match, and there are around 2 months of matches. So there are a lot of matches per season, and there are 11 seasons of data. So we have a lot of data collected with matches and balls, two data sets which we have imported. We have imported deliveries.csv in the balls data frame and matches deliveries in the matches data frame. So here you can see the columns that are there, but this is just delivery by delivery and match by match. So if it is DF matches, it shows which team was playing against which team and in which stadium, and who won the toss and something like that, and then how each match went through and how each ball resulted in. So there's nothing over here like who's batting on which number and what is the current score in the match. There is no match situation data. This is just ball by ball data. So there is a high scope of feature engineering in this data set, which we will be doing. So if we assess the data quality of this data set, the data contains high amount of nulls in columns like dismissal, kind, and player dismissed. So as I said, in the deliveries data frame, there is a column that is dismissal kind, and there is a column that is player dismissed, but not a player doesn't get dismissed on every delivery. Some delivery may result in just 1 run, 2 run, even 6 or 4 and 3 runs. But generally, there are 10 players playing in a team, so there can be at max 10 deliveries that a player gets dismissed out of 120, and that is the maximum range. It doesn't matter. It can be 1, it can be 0 also. So we have to treat them and we have to give them a standard value. So another thing was there are multiple stadiums in India and matches are played around the country. And by the time this tournament has progressed, Bangalore has been turned into Bangalore, and some other states have been turned into some other states. So they have been renamed, and the stadiums have been renamed, and some of them have error in the data. So if there is an abbreviation for some stadium used in somewhere and a full form used somewhere else, that we have to correct. Next thing is we don't have a specific data for any player in our data set. So we just have the names of the players and we don't know how that player has been performing in the past and what are his stats, may it be a bowler or a batsman. And we do not have a total column for the matches. So if we don't know how much total did a match actually output. So we don't know how much total was made by the first team batting in a single match. So we had to generate that. So I'll just jump in the IBM Watson machine and show you this project live. So there are a lot of imports in this. We will be importing a lot of files. So this is our first file. That is the matches dataset. And as you can see, each team playing, which date the match was played, which season it was, and the result, who won and winner, all that is there. And there are a lot of nulls in the umpire 3 fields. Umpires, it doesn't matter in our prediction dataset because we are going to predict the total. So there are a lot of fields that do not actually matter in our dataset. Same goes for balls. So we can see there is match 1, innings 1, the batting team, the bowling team, who's the batsman, who's the non-striker, the bowler, and all that data, and what actually happened on that bowl. So what was the result, total runs, and as I said, player dismissed and dismissed kind, and fielder are a lot of not null values. So as I said, we'll be fixing the datasets. So here we actually fix the datasets doing the value changes. So if we have M. Chinnaswamy Stadium, we change that to a standard value. We changed Bangalore and Bengaluru to a standard value. We changed Chidambaram Stadium to a standard value. So we remove the nulls, we replace them with an NA string to give them just a standard value. So once we have created that and we have fixed the data frames, now our feature engineering steps start, and you can classify this as the extract, transform, load stage with a lot of EDA involved. So we over here we have created 2 or 3 new data frames. So one data frame is for the man of the matches, as we were able to find. So we created a data frame that is which player has won the most man of the matches, which player has been the highest run getter or been the best batsman. Oh, my internet connection is gone. Okay, it will be connected. So yeah, actually I don't need it for now because I've loaded my Python notebook. So my data frame containing the batsman data I have acquired, and I have created a data frame that contains all the data about the batsman, the historical data, and how good a batsman is. So we never knew if the batsman playing is good or bad, but we can now know through this data. Same has been done for the bowler data. So there is the bowler data set. So we now know how much. So this has been done through group by and aggregating and all that. So we now know which bowler has taken how much number of wickets in match, how many number of matches he has played, and averages and all. So we have created 2 data sets, and now this is just for getting the unique number of teams and unique number of batsmen and bowlers, and this will be used afterwards in our prediction. So next we are going to do some EDA. So there in cricket there's a thing in the past that has shown some bias towards the team batting first or the team batting second. So I can show this over here. We check that, and how we check that is if it is biased through any team. So we see over here there is a difference in Bangalore, Hyderabad, and Jaipur and Kolkata. So these are the teams in which the teams batting second won more times. So if you are winning the toss over here in these grounds and you take the batting second, there is a lot of biasing in this, and this is generally because the dew factor comes in cricket, and teams batting second generally win. They are able to chase better. And the opposite has been shown in Chennai. So Chennai, the pitch is very dry, and the teams batting first generally win, and it's tough for the batting team second to win in Chennai grounds. Second, we'll check for which team has shown some bias to the grounds, and as over here we can see that Bangalore has shown bias to Bangalore. Over here you can see Royal Challengers Bangalore, and Mumbai has seen bias to Mumbai. Over here you can see Kolkata, 45 matches won in Kolkata. Similarly, but you can see all the home teams showing bias to the home grounds. Let me show you over here. So my result over here was that there's an equal fight in Pune. Every team was showing a bias to the home ground, but in Pune there was a near equal fight. But still, it doesn't show any clear statistics or clear insights from this, so we can get that home team favors the home ground. Now we just get to know the best batsman according to man of the matches won, and the best bowlers according to the man of the matches won. So that is part of my EDA, all the exploratory data analysis, to get to know the data better, to get to know the best batsmen, to get to know the best bowlers and the grounds and the teams better. So once we are done with that, what we can do is we can create a new data frame, that is DF balls, and this is more ETA than we have done over here. So we'll be going deep into the extract, transform, and load phase, but this we have done in a separate file. So we have loaded a file called IPL utils, and we have this function from IPL utils create balls extended, and we have used this extended data function, and we have fed our DF balls data frame, and we get the DF balls transformed data frame, and that actually concatenates all the users data for us. Let me show you if I can. So I have placed all my files on GitHub, and all the code and everything is in GitHub on. Yes, so as I said, my files are on GitHub, so you can just go to my GitHub and fetch all the files required, and I have the deliveries and matches CSVs over here, and the ball CSV that has been transformed through the ETL process stored already over here. So I won't be rerunning the code because it's a hefty code and it loops through every row in the data set, but we can directly fetch it from this file. So while it opens, I'm going to show you that how this data frame is going to be created. Actually, what is the result data set? Our result data set basically contains all the columns from batting team to bowling team, and the batsman, non-striker, and the batting data and the batsman and the bowler data that we collected. And to add to that, we have added one column, that is the total runs column. So sorry, not the total runs column, it is actually the score column, score and wickets fallen column. So this is aggregated data, and as you see, if a batsman hits 4, score turns 4, but the total runs is still 4, and the total runs for that ball is 2, but it adds to the score and it becomes 6. Similarly for the wickets fallen, if any wickets fall in any ball, so if for that match the wickets fallen column will turn 1, 2, 3, and it will be kept on increasing until the 10th wicket falls or the match ends. So I can show you the code over here. This is the code that actually runs through every row, and it's not that interesting, but it basically aggregates all the score and the wickets, and it also added the last wicket ball, so when the last wicket fell, and when the last how many wickets have been fallen, create score column, place last wicket ball, and create non-striker runs. This is just creating new data for our column. This is a lot of ETL process and lot of creating of new columns and feature engineering involved in this. So next, we again, as we have loaded our data set, we have to fix the NAs. So to the final task, our predictions. Now that we have our data frame with all the match situation data that we actually wanted, what is going on in the match, and if it's ball 1 or ball 2 of a certain over, what is the current situation in the match, we've got that. Next, we segregate our data into 2 innings, and we get the first innings data that from our data set, and we create a new column called total score, which is the total score for that match, which will be our label column, and which will be our Y for all the independent columns. And here we again define all players unique and all teams unique for label encoding. We'll be using label encoding because if we use one-hot encoding on our player dataset, so we have around 500, 600 players, and we have a lot of teams. So if we use one-hot encoding, the sparsity of our matrix will be very, very high. So we use the players dataset to label encoding on the players dataset and the teams dataset. So I've used 2 label encoders, one for players and one for teams. Once I've encoded this is our final data set that we can use for our predictions. And I have tried many predicting models, including linear regressions and naive Bayes regression, but the best fit for that, this model is random forest regressor, because it is an unstable model, and our data is pretty much unstable because cricket data is not that stable. Anything can happen on any ball. There are too many possibilities. So we'll be using a random forest regressor only. So we first try to find the best possible features, and this is a very interesting result. So our total score, which is the Y we have Y this. So our total score depends a lot on the penalty runs in the over, the batting team, and the bowler match wickets, and these data. So in the end, we were able to find out that our model basically depends a lot on the penalty run. So if a bowler is very disciplined, then the score will be low or high depending on the discipline of the bowler. If you don't give a lot of penalty runs, then the score will be relatively low, and if you give a lot of penalty runs, the score will be high. And that's a really good prediction. And it actually does not depend on the non-striker runs, because yes, he's on non-strike, he's just going to run. On the innings, because innings is 1, so it doesn't depend on that. The last wicket ball, it does not depend on the last wicket ball, so it doesn't matter if the wicket has fallen in the same over or in just the previous ball. It does not matter on the score. It does not matter on the bowling team. It does not matter on the batsman runs. It does matter on the striker runs, although a little bit. But the main criteria is what is the score, then who is the batting team, what is the over, and what are the penalty runs. This is a very good description for deciding our total score. So yeah, that's just feature engineering. And then we use our standard scaler, not min-max scaler. We are using standard scaler for transforming our training data set and feeding it to our random forest regressor with 100 estimates. And we don't use pruning techniques over here because we don't have much of overfitting. If we do use, I've tried, so if we don't get much overfit data. And to add to that, I want to say that I've used custom accuracy. So if I can just show you this. Yeah, I have defined over here the custom accuracy. This is if we use mean absolute MSE, mean squared error, or mean absolute error, that will also be fine. But I just wanted to show that how much correctness we have obtained from our data set. So I defined a custom accuracy that takes it to be a positive If we have, for example, we predict 165 and the runs are in within a threshold of 10 runs, so we'll be providing 10 runs threshold to this function. So it will be positive for our prediction if it's within the 10 runs frame or the 5 runs frame within the threshold frame, just to get a good idea of how correct we are. So I again plot the feature importance and it's the same. And for in the training set, we have got an accuracy of 98.11%. That seems really good, but you can get some indication that it's a lot overfit over here. But when we test it on our test set, it's a 86.2% of accuracy, and that is really good as compared as if we see cricket is a very unpredictable game. You can't predict anything on cricket, and to get this kind of accuracy is really nice. And if we check our predictions are very close to the actual marks. If we see over here, for example, if we see general score goes from 180, 190, 200, but 263 is kind of like an outlier. And to reach that outlier, our model has tried its best. So 215 is really a good attempt for our model to go near 263. But if we see 156, 163, 165, so we have got some really close results from our data sets. So this has been a good prediction. I'll just go back to the PowerPoint and finish my presentation with some results, which I've already shown you guys. So my feature engineering was missing values were given standard representation, new data frames were created, new enhanced data created with real-time match situation from ball-by-ball data to player stats. And yeah, we have used label encoding for categorical features. So as I've shown you, I've created a custom accurate results. So our results, as you can see, that discipline in the bowlers is the secret. So if you give less penalty runs, your score will be less. If you give high penalty runs, your score will be high. That is a very impactful result. We have got 93% accuracy on the test set. This is if we rerun the code on a certain random state, and it will vary from every run. So we have to set a random state for this. But this is a really close result. Conclusions: our data set was clean. It was explored and visualized many new data frames for the players and data and match situation data. Created and integrated. For feature engineering, multiple nodes were trained on best selected for regression and high accuracy models. Model predictions obtained with important feature informations. So that was my presentation. Thank you so much for listening and understanding. Thank you.